Thank you. I'm Byung-Tak Jang. My talk will be a little bit perspective and not very technical today. As the title says, in what direction we should do in AI, what has been changed during the last decades, and what might be the future. So it's a typical trivial question, actually. So what is intelligence? Recently, many people are working on AI, but I think sometimes we don't ask the fundamental questions. So let me see, let's see the video first. Here is a Robot competition, typically annually held in AI conferences. It's a RoboCup. So the robot should autonomously navigate the space, and sometimes it gets a mission by from the person, and understand the language and execute the instruction, and also have understanding of the environment by perception, visual perception mostly. So this is a complete intelligent agent working in the real environment. So that might be the dream of AI researchers, but we are not yet there. The video I have showed you, actually that's the winning team. SNU won the 2017 RoboCup competition. But to be frank, much of the intelligence the robot has here is programmed, not fully learned, partially learned. Of course, object recognition and some kind of motion control have been learned, but the whole task, the mission, and so on, the scenario, the long-term mission was not really learned. So that means when the environment changes, or the objects or the people around there, furnitures, when those environment changes during the task, it cannot solve the problem. Still, so that may be the general intelligence. So in a broad sense of the term, the intelligence should be involved with achieving long-term goal in uncertainty by solving problems. Here, uncertainty is very important, and solving the problem is important, and long-term goals. To do that, it should be able to perceive, reason, and act in a dynamic environment. The dynamic environment gives always a new uncertainty. Formally, we can just write the task of a function of the agent as a f of x gives y, where the w is the model or program or knowledge in AI in general. Given some input x, it just produces output y as a function of some knowledge w. So how do we solve in general that problem? You have the environment here, and the agents have the cognitive capability, and usually the full agent should be able to act on the environment and can perceive the environmental state so that it can decide the next action. So during the last 70 years of AI research, actually we have, I think, tried two different approaches. The first one was a programmed intelligence, how we put the agent intelligence. So the easiest way and pursued during the first 30 years of AI was the rule-based systems. Here, human knowledge is programmed into the machine, computer. And it was very successful in expert systems. Sometimes it's called also classical AI, GoFi, good old-fashioned AI, and symbolic approaches. It was successful, but has some definite limitations, but still in some way it's used actually. In conversational agent, sometimes people program the agent by rules so that they can respond very quickly and correctly. The limitations of this approach was there is no real perception, no real action. Only the input X and output Y are symbolically coded, and the only knowledge or model is in the rule base. So people program in terms of rule base. So many rules. If this, then that, and so on. So that was the first approach. The second approach, the level 2 AI, we can call, is the learning approach. That's the currently very popular approach. So here, deep learning is maybe currently the pinnacle of that machine learning approach. Here, instead of putting the human knowledge into the machine itself learns automatically from data. So this approach is learning from examples and kind of automatic programming. So like a large scale language models of like a GPT-3. So given the data set, huge data set, the model program W is automatically generated by learning algorithms. But usually the data comes from external agent or usually humans. So humans should provide the good or many big clean data. But in some sense, it's automated already because the humans do not provide the knowledge itself, but only the data to learn, to feed the data to the machines. So we all know that learning algorithm, how the learning algorithms work. Basically, it's a supervised learning, but unsupervised learning can work similarly if we put input and output the same kind of autoencoder. So generally, given some data set, the learning model produces some actual output, and compared with the target output, that's the error or loss function, and the loss or error is calculated so that the weights, the model parameters can be modified to reduce the error. So that's the derivative of the error with respect to the usually the model parameters. So in any way, generally that kind of error correction style of learning algorithms are universally used. The gradient search based algorithms are universally used now. And even in deep or many layer neural network style of machine learning models, we can do that. So given input and output, and the learning algorithm can generate automatically the huge complex models from the data and using a lot of computing power. So it's well proven that deep learning can solve many interesting problems. Recently, one example by Google here, given some language description of some photo, and the machine can generate the photo. So it's like from text to image translation. So the very realistic photos can be generated. That's very interesting. It's only from the examples. And many deep learning algorithms or learning approaches recently can generate, given almost any input, X, or any kinds of input, or almost any kinds of output. So extremely, from input can be image, and image to image generation, or input can be image, output can be text, or the reverse, or text to text. That can be the machine translation or conversation, chatbot, and so on. Anyway, during the last decade, most deep learning algorithm has shown that we can produce almost any given input to almost different kind of complex output if we have enough data and enough computing power. But there are many limitations. At the start, I have shown you, actually I asked the question, can we build a artificial general intelligence based on current approaches to AI? I think it's no, based only on the current approach. That's my argument today. And we will talk about what might be the better approach. First, anyway, the current AI approach's limitations are we need a big data. And usually having a big data is not easy, difficult, time-consuming, expensive, sometimes impossible. We also need some feedback. So usually we need external teachers. And most AI problems solved by deep learning style of algorithms are kind of a snapshot. From AI, in general AI point of view, it's not really intelligent. Given some image, I can say it's a dog or a cat. It's a hard problem. Actually, it used to be a hard problem, but it's not very interesting AI problem. It's just object recognition. And we don't say much, actually, if children do that, you don't say that child is so intelligent, right? But it's a very important and industrial problem. It used to be a very important problem, and we can now solve it. That's good, great. But coming back to the original dream of AI, human-level AI, I think we may still stuck in some local minima. So also some challenging. So most of the deep learning style, batch style learning models are not really grounded in the problem space or environment. Also, the environment is not stationary. It's always changing. I have shown you the robot moving around in the home environment. So the environment is changing. And most approaches are assuming the closed world. The world we are dealing with is closed. So I think AlphaGo is a very good example. AlphaGo is really excellent, but it's possible because it deals with the closed world assumption. And kind of some, a little bit not really stationary, but almost. Because while playing the AlphaGo, it's a simulated world, digital world, closed world. And you do not have any chance of moving wrong piece. So to go to the more real world, so AlphaGo has two sides. One is an excellent AI demonstration, what we can do based on current machine learning approaches. On the other hand, AlphaGo algorithm can fail abruptly if we add on some more uncertainty, like piece moving using robot arm so the algorithm might be very brittle. Brittleness has been a really, really big problem in AI history. And machine learning has solved partially that problem, but not really yet. So once again, what is intelligence? Can we build an artificial general intelligence? So to go further, maybe we need some more autonomy, especially in learning autonomy. So we need to go to the autonomous intelligence. So the agent here can observe in a real world, the agent should be able to interact with the environment by perception and action. And it's important it's in cycle, not just the perception, not just the action. It's very important it's in a circle. So, and the agent can actually generate the problems itself. So here we can add another function. Given y, it can also generate the training, learning data. So it's a kind of active learning. In the history of AI, already machine learning, there was some research early on already, active learning. That means that the learner decides what data it learned, not just the passively adjust given the data set, but the learner can actively select the data set to learn, or it can very actively generate the data set as well, conceptually. That can really sometimes work in closed world assumption as well. But to be more general AI, I think we need that kind of self-teaching approach. Self-teaching can generate the problems as well, also can evaluate its own performance. So usually in current machine learning approach, objective functions are already defined and fixed at the start. But in real world, maybe the objective function should be adjusted as well or modified. So that might be the another direction. So to summarize, to go further to human level AI, how we empower the intelligence to the agent. I have summarized the two approaches, and now I will go to the next approach, which is embodied intelligence. So the first one was a programmed AI, symbolic approach, classical AI, and typically rule-based systems where rules are provided by the humans. It's a human-programmed AI. The current AI, as I said already, is a learned approach. It can do much better because the learner can itself improve its performance based on more data. But the real problem is that who provides the data? Still not the learner itself, but only external humans or other agents should provide that. So so to have more autonomy, the agent should, one approach is the agent is embodied. Embodied means it has the body. To really understand what's going on underlying the intelligence, we can maybe go back to the evolutionary time to a single cell organism. Evolutionary, we all humans, animals, other animals came from there. So what was the basic functions of the intelligence? It's a single organism. Here, the single organism has the body and has to move. The most important intelligent behavior is to go to the prey and eat it, or escape from the predator or far away from it. So deciding, this is called fight or flight. It's all survival, so it has to eat or escape. Maybe the human brain or other cognitive functions evolved from that primitive functions. Understanding the environment and move in some direction. So it has to decide in real time, very fast. Otherwise, it cannot survive. And even, I think, though humans evolved, sound 같네. Maybe, sorry. I will try this way. Even humans evolved from that kind of primitive organisms or animals, but we still have that kind of primitive functions. So you have to be very quick to recognize the danger and act to escape from the danger. And in AI, we have studied a lot of language and vision problems. But why we need that kind of the AI to really understand human language? You need to really understand the relationship between language and action and some other things. So all the philosophers and linguists and others have found it already. And AI, I think, should embrace that kind of a foundational knowledge into our future AI systems. That's okay. In the interest of time, I think I need to stop here. Anyway, all the important intelligent decision making, even in higher order humans, are based on the action in real world, in environment. So, but AI has forgot that. Especially all the AIs has ignored all the environment. They ignore the perception, they ignore the action. Just a thought of the language and the symbolic representations. Only recently, when the machine learning and especially deep learning came in, we start to think of the sensory data, which is related with the environment, but not directly, only indirectly. We always collect the data and try to learn. I think we need to abandon that approach. Collecting the data and try to learn is a partial, can only be partially successful. To really intelligent, for the agent to be really intelligent, it really need to do the perception, action, learning cycle. At the right moment, we are learning very different things. We are not just collecting and go to the room and process that and learn later. We do all the time. So the humans are living in the environment and interacting with the environment and sense that, and based on that, you recognize and again act and see the response and take the next step. So basically, intelligence is learned in interaction with the environment, with the body. Because a body is there, we always feel and perceive the environment. So embodied cognition. Cognition is embodied and collected by perception action cycle. And all the knowledge we have is grounded with the real world and the real environment. But if you see how the deep learners are learning now, for example, Siri, how the Siri learns, Alexa, they just learn from just the text, language only. We are cheated by them. They are intelligent because when we hear some words, we actually use all the knowledge we have collected embodied in our brain or mind. But the current AI or Siri, they just use the language only. Maybe, but recently there are some conversational agents that can use images as well, or image generation. But still, in comparison to how humans learn, even children learn and do, it's only partial, fragmented aspect of the knowledge or data. So it should be grounded with the body in the environment. So in that sense, learning by doing is really, really important. So the agent AI should be able to sense and act and interact with the problem domain. Then it can maybe solve better the uncertainty coming from in the real world. Uncertainty is the most, I think, a foundational capability the AI should be able to deal with. So continual learning is foundationally important because everything changes and you need to learn every time and try to deal with the uncertainty. So philosophically, probably this embodied knowledge emerges as some kind of agency or self-consciousness. So it's very much a philosophical words, but to be a human-level AI or more general AI, I think that kind of functional properties might be foundational. Without that, maybe a general intelligence is impossible. So anyway, we need to think of the world, environment, not just the agent of itself. So once again, when we have a body and we can have more sensors and actuators, gives us more autonomy in terms of feedback. And that means we can have a more learning experience, which gives broader general intelligence. So if I have hand and eye, so I don't need to ask how heavy the table is. I can try to lift the table now, right now. I cannot, so this is heavy. I know without any help from others because I have my actuators and sensors. I recognize that I cannot lift this table, so I know this table is heavy or fixed. So that is impossible with the current approaches to machine learning, right? But very easy if I have some kind of actuators and sensors. So by embodied AI, we can do much more, go further to more general AI intelligence. So we can generate the data, not just wait for something is coming. We can also self-feedback. As I said I can get my feedback already from my eye and from my hand. I do something and my eye can recognize it. So self-feedback is possible. So that means it can continually learn. And from that, language and vision, they are grounded. So cross-modal, multimodality, multisensory informations are grounded each other. And so when one is missing, another can complement. That's how we can do something generally. So, and it can hopefully deal with the non-stationarity and also in open world. So it's more autonomous, more cognitively capable. Now, so far so good. We know that when we have the body and sensors and actuators, then we can do better. So from machine learning aspect, but we cannot program everything. So manual programming is impossible to create a general AI. So the AI should learn itself. So the embodied approach may be a new approach from, so far we have done machine learning, then we need to go to learning machines, meaning that the learners are capable of sensing and actuating, so having body. So we can think of this is theoretical, but universal learning machine, which is fully autonomous learning machine that improves its performance without human intervention by perception action cycle. And so it's a really recursively self-improving system, continually improving itself from interaction with the environment or working in the task domain by sensing and actuating. So the basic elements of a ULM, Universal Learning Machine, should be, of course, the model selection problem. The program size of model should be able to be designed automatically. This is already done in deep learning. Already, we have AutoML style tools and technology. This is already done, but we need a lot of computing power. But we have enough power, I think. And the data acquisition, that was the issue of limitations of previous approaches. And if you have sensors and body, self-teaching is possible. One further step to go to the general AI, I think we need the objective function adaptation. Because the change environment is changing and there are so much uncertainty, even the objective function should be able to change. That's a meta-level intelligence. Meta-level intelligence, meta-level, and maybe learning too. So it should be able to think itself, self-reflect, meaning that what should be learned and what task is missing and what I'm doing well and what I'm doing strong. And that kind of meta-knowledge can be obtained as well. So in that sense, the ULM is a prerequisite to achieve a human-level general intelligence. It's necessary, but maybe not enough, sufficient. But at least it's necessary. So practical research question. So this is, in my lab, we are pursuing every day. Can we build a machine that learns 24/7 continually without any human intervention? So in most AI labs, the learners are taking rest without any data given, right? But the learners can continuously learn. Hopefully, that kind of tasks. I think we have seen very good examples from the previous talk as well. Here is maybe continuation. This is, again, the RoboCop. And there are very interesting scenarios here, like a grocery task. So all the tasks are related with some mission, not just a fragmented simple task, but a sequence of actions to achieve some goal. And to do that, it should understand the environment and move around and act, which involves with very much uncertainty, dynamic environment. So this is a dishwasher task, for example. The robot should get the dishes and put it into the dishwasher. So another task. Some other tasks are Shake Chef. Like it can make orange juice from the fruit. Another one is some like small shopping or cleaning. Right. That kind of tasks are done already. That video is actually won the second place in 2019's competition. Again, all the tasks were not fully autonomously learned yet, meaning that when we change the environment or the objects or space, the agent or AI can fail. So to be robust, it should learn itself by failing and by doing or by experimenting itself. And it can try different things and recognize itself what was wrong and or what was good. And based on that, it can learn further. So one first step to that direction of research, we tried this. This robot actually collects the toys and clean it up, put in the box. Sometimes it does good, but other times it fails to grasp the toys, but don't know it failed to grasp. So sometimes it foolishly do some moving task, like now. Without toy, it carefully puts something in the box. That can be corrected without help of a human, because the robot agent has the camera. And of course, it should know that the arm or the hand is empty, but basically it has a camera, it can recognize it. So from it can avoid the, okay, I think that video is coming. The next video is not coming, sorry. Okay, yeah, here. So by having another capability of knowing that it's not doing well, so it can self-evaluate its performance and do the next thing without wasting the time. So it's an additional level of autonomous learning, which is possible by the perception action cycle. That is it, because it's embodied. Okay, that's one example. And actually, the technical process of recognizing how the agent itself knows what's failing. It can have many diverse sources of sensors, and based on that sensors, it can recognize it and correct it. Also, it can repeat the correction process by learning trials, meaning that so one more direction to the autonomy. Those kind of tasks can be tried in many different tasks. Of course, it's robotic manipulation, very natural because robots has embodiment, perception, action, and typically, naturally, they can do, like doing cooking or pick and place or some simple cleaning tasks or drawing the pictures. So those are natural embodied intelligence tasks, of course. And but we may actually go further beyond the action, as we have seen this video again. Not just the action or move. We need to have really human level intelligence, like a language capability and knowledge, some kind of higher level intelligent function as well. When they are grounded in action and environment, the language capability of the agent can be also human level, hopefully. So so far, very separated. The language research and robotic research is separated, but in the end, to go to human level or general intelligence, both should be combined so that the language actually understand the action as well. And that's the way to go. As a simple architecture. So in that sense, the agent should have internal simulation as well as our brain has. We do something, and then at the time of doing, we already expect the next future state while doing. And we can learn from predicted error. It's now well known in machine learning community. I do prediction, and based on prediction error, I can learn it myself. And that's a very natural if you are embodied and learning by doing and by perception action cycle. So, but internally, we can do the internal simulation as well. That means we can predict the future at the present. And the future already has the present has, in that sense, the recurrent cycle, and actually the present already has the information of the future. Not just the past, but also the future. Predicted future is here because of the internal simulation. That kind of architecture is very important. I have to skip here, but we basically start with some initial model of a perception action and the transition goal as well. We do act, and at the same time we predict, and internally we perceive by internal simulation, and also correct and evaluate. And this is an internal loop, internal simulation. But if you are embodied, you can also physically perceive. Camera can do that already, and also learn by learning by doing. And also, you can self-reflect and try to modify your own goal. So that's again the self-reflection capability. And that completes maybe the recursively self-improving learning. So we are not done yet, but that might be the general direction to go to the really human level. It can be implemented in embodied agents, which can learn continuously. So let me summarize. AI during the last 7 decades, I think we have experimented with the 2 big paradigms. One was the symbolic AI, programmed intelligence approach. The next one was the sometimes called the connectionist AI or learning-based approach, learned intelligence approach, as I said today. And the next level will be the more cognitive approach, embodied cognitive approach. It's really working in the real world, not closed world, but open world. So in the open world, it can continuously learn or explore the environment or the domain or the task so that it can improve itself without help from the external teachers. I think we are now in the level 2 where deep learning can automatic programming based on given data set, if the data set is enough. But the next level should be the learner can generate the data set itself and self-teach itself. The next level might be self-reflective systems where the goals, objective functions should be tuned as well. That's the universal learning machines. And then maybe we can be ready to achieve the human level AI, AGI. So self-teaching and self-reflective capabilities are in some way, I think, a prerequisite for human level AI. And to do that, embodiment is really essential. So AI as embodied cognitive systems. So far, AI has been just on the software side, the mind side, the data side. But we need to go to the real world and work with the real world environment with the body and sensors as well. Then sensors means just the data. So to learn new knowledge. So that's the direction. And okay, so I can finish now here. Thank you.